I am Dr. Muralidhara B., Government Engineering College, Muslevasalli, Department of Mechanical Engineering, which belongs to Hasan Talukan district, Karnataka State, India. My contact number is murligck@gmail.com, 7598972621 94482752260. I have done few papers, publications, and journals with my colleagues and friends and my research guide. This is a paper where we studied the effect of fiber architecture on the mechanical properties of the carbon fiber epoxy composites. The abstract of the work mainly consists of investigation based on carbon fiber reinforced epoxy composites addressing the effect of fiber architecture on the mechanical properties. Mechanical properties using T800 carbon fiber epoxy, T700 carbon fiber epoxy, and T300 carbon fiber epoxy investigated composites investigated for indentation, in-plane, tensile, and bending loads. The composites were fabricated with equal weight percentage of carbon fiber, similar consolidation process using hand lay procedure followed by compression molding method. The effect of fiber weave architecture on the mechanical properties of the carbon fiber epoxy composites is more obvious than in neat epoxy. Both the tensile and flexural results showed that T800 carbon fiber epoxy composites has evident strengthening effects on the tensile and bending load response. Also, fiber architecture marginally affects density and severely affects strength and deformation. Here, the composite performance is dictated by inherent properties and fiber weave and structure. Even with fiber flaws, porosity, defects, stress concentrations, the weaving pattern is so beneficial that it makes composites to be more or less sensitive to flaws. Finally, mechanical properties further were assisted using the SEM, that is scanning electron microscope. The key literature consists of carbon fibers present exceptional advantages in strength-weight relation, affect mechanical properties, materials lectures, which was studied by X. Liu and team. The impact of carbon fiber architecture on the mechanical properties of composites, especially two failure modes critical in designing with delamination, flexural failure, and polymers. Carbon fiber epoxy composites display higher mechanical properties, studied by B. Petro and team. Common fabrication induced flaws and defects with corrective actions to improve sample quality, studied by U. Farooq and P. Mala. Number of laminae in composites and fiber orientation affect mechanical properties, studied by H. Ramani and team. Proper composition of polymer arrangement is essential in structural composites, studied by JMFD, Paiva and team. Torres size T800 carbon fiber epoxy composites had higher mechanical properties, studied by L. Wang and team. Mechanical and dynamic mechanical properties of fiber reinforced composites improved significantly with increased fiber component, studied by W. Liu and team. High strength carbon fiber in comparison with steel and other carbon fiber has higher ablation behavior and thermal stability, studied by M.R. Firmonesh and A. Azur. Research gap. Less research work on carbon fiber epoxy composites have been observed considering different carbon fiber architecture. Less research work on 1201 carbon fiber, that is the hybrid carbon fiber epoxy composites. Then PMC structures fails in fluctuate, and hence development of new fiber structure with improved flexural properties needed. Impact of 2x2 12 carbon fiber structure on mechanical properties for best results. We want to compare and study it. Plan of action: selection of matrix material, reinforcement material, fabrication using simple hand lathe method followed by hot compression press, test samples cutting from fabricated laminates according to ASTM standards, mechanical properties test, microstructure study through SEM. Method of fabrication: selection of matrix material. First one, epoxy resin, Ararat LY1564, hardener Aradur 22692, and the epoxy resin hardening mixing ratio by weight percentage was 100:25. Selection of reinforcement material, carbon fiber will be bidirectional twill T800, T700, T300, and the combination of T800, 700, T800, 300, then T700 and 300. Twill structure, why we selected means pattern is elastic, weave is loosener and good for complex shapes. The composite composition studied where T800 carbon fiber alone with epoxy, T800 alone, T800 alone, then T800 and T700, T700 and T300, T800 and 300 with carbon with epoxy. This is combined composites. The carbon fiber and epoxy by weight percentage remain the same, 60% by weight percentage and 40% by weight percent respectively. When it comes to individual carbon, only one carbon fiber, it is 60%. It is 60%. When it comes to combination, we selected 30% plus 30% for each of the two carbon fiber. We use the simple hand lab method in order to obtain the required fabricated composite material, followed by the hot compression press, nominal liquid percentage and identical concentration for all the 6 types of carbon fiber except composites. Compression used was 0.5 megapascal, cured 24 hours at normal room temperature, then we cured in oven, air distributed one for 1 hour between 90 to 100 degree. Laminate size was 300 into 215 into 3 millimeter. Test performed the mechanical properties. Mechanical test performed were interlaminar shear strength, hardness using Shorty hardness, tensor properties, strength and modulus, flexure properties, strength and modulus, impact strength. The ASTM standard studied was, or procedure obtained was these things: ASTM D2344, D2240, D638, D790, D2560. Microstructure study. Study morphology and fracture surface of a specimen, model GL JSM 6480 LV SEM with a 20 kilowatt acceleration voltage. The results and discussion, mechanical properties. If we observe the graph of the composite combination versus the ILSS, that is the interlaminar shear strength, we can see that T800 composites provided maximum property, maximum values. Low values were observed in T700 and T300 individual composites because there were increment in wide fraction in composite, which results in decrease of adhesion among the fiber and the matrix. Here we used 3-point short beam test, bending test at a cross-set speed of 2.5 mm per minute. Next, the hardness. FT300 and FT800. FT300 and FT800 represent the surfaces of T300 and T300 and T800 surface of carbon fiber epoxy composites, hybrid composites. Likewise, T800 and DT700 represent surfaces of T800 plus T700 carbon fiber hybrid composites. Likewise, ET700 and ET300 represents the surface of T700 and T300 carbon fiber hybrid composites. Shore durometer tester was used. Maximum values was observed in T800 composites and lowest was observed in T700 composites. Maximum value obtained for composites. It was also observed that in the combined composites, the maximum values were obtained for composites made with T800. Tensor properties. We can see the graph here: composite versus the tensor strength and tensor modulus. Left, you can see the tensor strength in megapascal, and right y-axis gigapascal. Young's modulus. The cross-set speed was 2.5 mm per minute while testing. Young's modulus varied significantly with regard to fiber structure. Here, number of layers involved during fabrication of composite did not perfectly influence the properties. T700 carbon fiber composite present the highest elongation, whereas the T300 carbon fiber composite showed minimum values. Flexural properties. Once again, here also cross-set speed of 2.5 mm per minute was observed. T800 composites provided highest value and T700 composites showed the lowest values. Maximum flexural modulus was observed in hybrid T100 plus T700 carbon fiber epoxy composites. Addition of T800 carbon fabric with T700 carbon fabric in hybrid composite enhanced flexural properties. Reason for low values may be the bond-like defects like cracks, porosity, voids, kissing bonds, etc., which seriously affect structural excellence in bonded joints. Impact strength. Here the cantilever beam impact estimation ISOT type was used, ISOT R3 hammer and 0 to 10.84 joules. Preparation of 45-degree V notch was done on the center of the specimen using notch cutter before doing the impact test. T800 T700 carbon components showed the highest value, whereas the T300 showed the lowest value. Composite made with T700 composite showed the higher impact strength than other composites. Fractured surface study. The SEM of tensile fractured surfaces, they show that T800 composites figure A and D, T700 epoxy composite figure B and E, T300 composite C and F composite showed that filaments of fiber completely enclosed with epoxy system. All these figures A, B, C, D show that the the fibers are completely enclosed with epoxy system, matrix system. No interface debonding, matrix delamination, cracking, etc. were observed. However, there is definitely there is difference in mechanical various mechanical properties, and also we can see that there will be differences. Maybe small voids may be there comparatively. There may be lesser voids in some of them and higher voids in others. So, figure D, E, and F show few evidence of fiber pullout and micro voids compared to T800 composite has less voids than others. Hence, it showed higher values. Likewise, in the sum of impact fracture surface, here also A, B, C, D figure shows that fiber elements are completely enclosed with matrix. However, D, E, F figure shows us a few fiber pullouts and micro voids. Compared to T700 composite, it had less voids than others, and hence it showed better impact property. Conclusion: T800 composite showed dominant mechanical property. However, its elongation and deflection difference with others were not significant. T800 composites also had higher interlaminate shear strength and hardness than other composites, and enthalpization happened where the flexural properties of T700 carbon fiber composites were lower than the other composites. Composite with T700 carbon fiber had higher impact strength than the other composites. Addition of T800 carbon fiber with T700 carbon in hybrid composites enhances flexural properties and impact strength of T800 and T700 carbon fiber composites. Also, the composite performance dictated by both inherent property of carbon fiber and weave structure. Even though new fiber flaws are introduced with less stress concentration, the weave pattern is still beneficial because it makes composites less sensitive to flaws. Also, finally, the SEM provided comparatively few proofs of fiber misalignment in the T300 carbon fiber and T700 carbon fiber composites, and strong combination of filaments that is observed at the toe region in the T800 carbon fiber composites, and hence T800 showed better properties in most of the properties. Finally, the acknowledgement. We thank NTT Tiruchirappalli, Tamil Nadu for giving opportunity to work on this project, providing experimental facilities. We also thank Center for Composite Research Laboratory, CCMR, NE, Mysore, Karnataka, India, and Dr. B. Suresha sir, Professor and Head of the Department. And also we thank Professor at the Mechanical Materials Engineering Department, NTT Tiruchirappalli, Dr. Kumresh Babu sir. Also thank ICMM 2019 at Vellore for giving the opportunity to present an article. I also heartily thank the team of the international awards of composite materials, which provided a great opportunity for me to present and to see that myself is exposed to the whole world in the form of the international award. I once again wholeheartedly thank the Composite Materials International Research Award team for nominating me for the Best Researcher Award. Finally, I thank my parent institute, Government Engineering College, Hassan, Taluk District, Karnataka, India. Thank you.